Hey everybody, what's good? Do people still say that? I realize you can't respond to me. Anywho, um, today we're going to look at a couple different ways of evaluating limits, particularly the diving out technique, rationalizing, and then a specific type of limit from calculus. So going a little bit farther. Um, and the reason we have these other techniques, these other ways, you might be thinking, why do I even need to bother with these? Because direct substitution is so much simpler. If I'm looking for the limit of a particular equation at a number, I can just substitute the number in, and I can get the answer. I got that. I can wrap my head around that. But the issue is that sometimes that fails. And we'll see that in this first example. If I'm looking for the limit of this particular function at just -3, if I go to do direct substitution right in the denominator here, that's where you're going to notice the issue. -3 getting plugged into here gives you 0 in the denominator, division by 0, and that's never okay. So if we go to a chart and we start plugging in x values around the limit, we start looking for around -3, we can see this looks like it's approaching -5 from the left, and it looks like it's approaching -5 from the right, but I just don't have an algebraic way of doing that. So we have this thing called the diving out technique, which is simpler than it kind of seems like it's going to be. You might be thinking, oh god, great, now he's going to make things like 10 times more complicated, and I'm going to go home and I'm going to cry all the time, and I'm not going to be able to pass, and I'm not going to be able to go to college. But it's going to be okay, because you already have all the tools necessary. Basically all you're going to do is factor the numerator. You have a quadratic on the top, x squared plus x minus 6, which is a pretty simple quadratic actually. So you're looking for factors of -6 that add up to 1, and when you factor it you get x minus 2, x plus 3. Now what's good about this is, and what should happen, is you have something that you're able to kind of cancel. You have x plus 3 on the top, you have x plus 3 on the bottom. So you get to this point where, strangely enough, you're saying that the limit of this bigger function as x approaches -3 somehow is supposed to be the same thing as the limit of x minus 2 as x approaches -3, and then you can do direct substitution. Then you can say, okay, well now I have a simpler function, x minus 2, I can plug in a -3, -3 minus 2, -5, which is what our table before was showing, is that it should be somewhere about -5. So how does this work? Why is this even a thing, and why is this valid? Well, basically what's happening here is this larger function shares every single point in common with the smaller function. So this larger function right here follows the exact same pathway as the smaller function, with the exception of one point, and that's at x equals -3. But the good thing about finding the limit at that point is that I don't really care what happens at x equals -3. What I care about is the behavior of the graph as it approaches x minus 3, both from the left and from the right. So if these two functions share all the same points, with the exception of this one, then their behavior as they approach those points should be exactly the same, regardless of if their value at that point is the same. Okay, so because their behavior is the same as they approach this point, their limit is the same as they approach that point. So I'm allowed to kind of factor the top, do the diving out technique, and simplify it to this other equation, which I can then directly substitute. Right? That might seem a little bit weird at first, but it's going to be really, really cool when you're able to solve some complex limits using that. Alright, so if you could all do me a solid and do exercise 15 from, this is 11.2. Number 15, we'll be using the diving out technique. So give it a try, see what you get, and hopefully it's not going to be too hard, and we'll be able to use this when we come into class. Okay, so the next thing we're going to look into is using a rational function, one that has square roots on the top or bottom of the function, and how we deal with that type of situation. Because again, we're going to have the type of place where we have an indeterminate form, basically. And what indeterminate form means is that when you do direct substitution, you're going to be getting 0 over 0. Okay, and that really has no meaning. It's the number 0. It's being divided by 0. Basically, it has no purpose being a number. So when we have something that has square roots, as you might remember in other times, what we had to do is multiply by that radical number to rationalize. Or if it was more than that, something like, say, x plus 4, you can't just multiply by the square root of x. You have to multiply by its conjugate, which is the entire, if you think of this as a binomial in a way, the entire binomial in its negative form. So that's the type of thing that we're going to have to do here. If we look at this first example here, we have the limit of this seemingly complex function as x approaches 0. Now, if you put in a 0 up here, you're going to get 0 on the bottom. And then up here, you're going to get 0 plus 1, square rooted, minus 1. So you end up with the indeterminate form, 0 over 0. And that's where you know you got to do something else. Direct substitution is failing you, and it's just not okay. So what do we got to do? Can we dive out? Can we factor the top and make things easier? Well, it does not appear that way. It appears much more complicated than that. And in reality, it's probably not going to be. It just might seem a little counterintuitive in a way. We're used to saying, I don't like having radical numbers in the denominator, I want them in the numerator. But what we're actually going to do here is do the exact opposite of that. I have a radical in the numerator, and in order to change up the function without actually ruining its integrity and ruining its value, I'm going to multiply the top and the bottom by the conjugate of the top. Alright, so I'm not sure how much of this is going to show up in this video, but somebody just walked into the room, and then I also got a phone call right in the middle of recording this. So it's craziness. Am I right? Live video recording. There's no one here to laugh with me. Anywho, what were we in the middle of doing? We were rationalizing, right? We were doing a little bit and multiplying by the conjugate. It was great. And I realized that time hasn't actually elapsed for you if you were watching this all the time that I had this paused. So you probably haven't lost your train of thought, except for the fact that I've been rambling. So let's try and recap. This was the original function, and what we're doing is multiplying by the conjugate on both the top and the bottom in order to take that rational out of the top. So when we do that, up on the top, what we're going to get is exactly what we wanted. That square root is going to go away. 1 times 1 is 1. And then on the bottom, we basically have x multiplying this whole thing. Don't worry about actually multiplying it through, because the simplifying piece and what we want to do with it is probably going to incorporate having those two factors separated. If you multiply it through, it's going to be harder to notice that you can eliminate something. So when we go over to the next page here, see, if you would have multiplied this x through, you wouldn't have been able to see, oh, there's an x on the top, there's an x on the bottom, I can divide them out. So don't do any unnecessary work for yourself and multiply it out and then factor it out again. Just leave it, because it might cancel. So we cancel out the x's, and look at this. Now I have 1 over square root of x plus 1 plus 1, and I'm still looking for the limit. So I can say that the original function, this one over here, is equal to this one that I kind of just changed around a little bit. I haven't ruined the structural integrity of the function itself. All I've done is rewrite it and make it look different. So these two things are equal to each other, and I'm still looking for the limit as it approaches 0 for either one of them. For this one, however, if I directly substitute by putting in the 0 here, I get 1 over 2, 1/2, and I get the answer I was looking for. Okay, so this is the second type of technique that we're looking at today, and it's, again, it can be really cool if we can kind of grab on to when we need to dive out, when we need to rationalize, when we can just directly substitute. And limits can be something, that are more like a puzzle, and they're more, fun rather than something crazy when you look at the notation here and you think that it's really difficult. Right, so let's see. If we take a look at what this function actually looks like, again, it's this one singular line with just a hole right there. So when we look and we try to evaluate at this particular point, we're not going to be able to get something because there's a hole in the graph there. But we can see from a table that it seems to be approaching 5. It seems to be approaching 5 from this side. So there, I'm sorry, 1/2. That seems to be approaching 1/2 over here. Seems to be approaching 1/2 from this side. And now we kind of have that algebraic technique of rationalizing in order to solve for it, instead of just counting on tables to try and figure it out. Okay. What I would like for you to do is to try, let's say, exercise 23. Okay, again from 11.2. This should be a rationalizing one, and hopefully it goes okay, and we can check it over next time. The last thing that we're going to look at is using technology, because sometimes the limits are just so sophisticated and so complicated that the particular techniques that we have here and the algebraic manipulation doesn't quite work because the functions aren't algebraic. For example, this function here, some of you might recognize this from when we were talking about exponential functions way earlier in the year, and we'll see exactly what this is supposed to be in a second when we finish. But the limit as x approaches 0 of this function, it's not an algebraic function. So we can try different things. We can can I factor it out? Can I dive out? Can I rationalize? And none of those things seem to really work, and using direct substitution doesn't work either. So really what I have to do here is plug it into my calculator and see my x values as they approach 0 from the left and from the right. What does it look like I'm approaching? And really, when you get to something like this, you kind of just have to take the two numbers that are surrounding it and find the average of the two to try and figure out what's in the middle there. And it's not very accurate. It's estimation. It's guessing, an educated guess. It's not perfect, but later on, when we have the tools to get the actual limits here, you would see that this function is, and the limit of that function as it approaches 0 is e. And let's just go back to that function one more time. You might have recognized it from when it was talking about compounding interest. This was the approximation of e. Way back when. Okay, and then kind of one of the last things that we want to talk about this time is a one-sided limit. Recently when we've been talking about them, we've been talking about what is the limit, the one limit as it approaches this particular point, meaning it's coming from the left, coming from the right, and they're both agreeing that it meets at this particular point. And we actually said that the limit does not exist if those two things don't agree and meet at the same point. Well, now we're going to look at it kind of on a different perspective and say, well, okay, maybe the actual limit doesn't exist, but what about a left side limit? What about a right side limit? From the left side, what's it approaching? What's the limit as it approaches from the left? From the right side, what's it approaching? What's the limit as it approaches from the right? So we have a little bit of a change in notation here, just coming from the left, we add a little minus sign. Coming from the right, we add a little plus sign. Okay, so if you ever see the minus or the plus, we're talking about a one-sided limit. And let's take a look at how we would look at that. If I have this particular function, absolute value of 2x over x, it's kind of like the example that I gave for when a function doesn't have a limit back in the previous section. Because as you can see, from the left side, it's approaching -2. From the right side, it's approaching 2. And so these two things don't agree. They don't say, oh, the limit from the left and the right is this one number. They have different left and right hand limits. So the left hand limit is -2. The right hand limit is +2. And that's all we have to do, is just kind of break it down into its two different things. And it's also possible that they both have the same left and right hand limit, in which case the full limit is that one number. But we can write this using the notation: the limit of x as it approaches 0 from the left of this particular function equals -2, and the limit as x approaches 0 from the right of this particular function equals +2. Alrighty, and this is kind of what I just glossed over, which is that if the left and right hand limits are the same number, so if it says, if in that last example we said the limit as x approaches 0 from the left equals the limit as x approaches 0 from the right, then the actual limit in general, the limit as x approaches 0, without positive or negative, not coming from the left, not coming from the right, just the limit in general as x approaches 0, that will equal these same numbers. So the limit from the left, let's say, is 2, the limit from the right, let's say, is a 2, then that means that the whole entire limit of the function is a 2. And that might seem intuitive. You might have already kind of gathered that information, but it doesn't hurt to throw it out there. And lastly, a limit from calculus. Now this might get a little bit confusing, and actually before we do, I do want you to try exercise 49, which is left and right hand limit problem. So do exercise 49 and then we can go to the confusing stuff. Yeah! Okay, limit from calculus. There is a very, very, very important equation, which is the difference quotient in calculus, and that is this idea right here. It's f of x plus h minus f of x over h. And you might have seen this. I believe I had you do an equation when we were looking at sine and cosine values, and it was simplifying a sine and cosine equation using this. And you might not have really taken into account that that's what you were doing. But this is a very important equation. It's called the difference quotient. And finding the limits of these types of things, you will notice becomes very big. So let's say we're looking at a function given by x squared minus 1, and I want the limit as h approaches 0 of this particular function. So what do I have to do? Now you might be asking yourself, where is this stuff coming from? And this is just being given to us. It's saying, this is my equation for f of x, and I want to find the limit as x approaches 0 of f of 3 plus h minus f of 3 over h. So this is given. Okay, so don't necessarily worry about where did this 3 come from, what's happening here. What we want to do is try to evaluate. Okay, so this is where we're starting. Now, if I have f of 3 plus h, that's basically telling me that every place that I have an x in my function f of x, I have to substitute 3 plus h, which is kind of weird, but let's go for it. Okay, so I have x, which is 3 plus h, squared minus 1. Okay, that takes care of the first part of it, f of 3 plus h. That is this when I expand it and I use the actual function. And then the next part says f of 3. Okay, well, f of 3 means I just have to put in a 3 into the equation, and I still have h on the bottom. Okay, now what about when I kind of expand this all out? Okay, when I multiply this binomial by itself, I'm going to get 9 plus 6h plus h squared, and I still have a minus 1. Right here, I'm going to have 3 squared, which gives me a 9. I still have minus right here, and then, yep, so that's all of that. Now when I move on to the next side and I simplify, let's take a look here. What can I simplify? I have 9, and I have negative 9, I have 1, and I have negative 1. I basically can get rid of all of these things. All I'm left with here, h squared and 6h over h. Boom. Now, let's try to direct substitute. Put a 0 in there. Oh, jeez. 6 times 0 is 0. 0 squared over 0. 0 over 0. Indeterminate. But I got tools now. I can do factor out, dive out. What I'm going to do, I'm going to factor the top. Factoring the top is super easy because it's just two terms, each with h in common. Factor out an h, and what do I get? H on the top and h on the bottom. Boom. Boom. Ah, this is just getting super simple. So basically, all I have to do, what I'm left with here is 6 plus h. Substitute in a 0 here. 6 plus 0. 6 plus 0 equals 6. The limit is 6. Okay, now I know that that can be a little bit difficult, especially this part right here. When you're substituting in, going from this value, these values here, to right here. That can be the really tricky part, and the part where you can make a lot of mistakes. So we got to be very, very careful about that when you try exercise 79. Okay, if you need to rewatch that part, please feel free to do that. We'll look at a lot more of them in class. So that's a couple of different techniques for solving the limits. And then next time we'll start actually moving into a couple of different kind of major calculus problems like tangent line and area. But peace out, y'all.